I have changed my title, so I hope you can apologize. You can forgive me. I have recently found interesting results from white binaries. So I thought that I can't miss these results for this important meeting at 50th anniversary. So, and also I already got a favorable referral report, and I have almost finished revision, and I'm about to resubmit the revised version. So I'll just collect the evidence from galactic rotation curves and white binary stars to show the convincing case that modified gravity seems real, and it seems like it's amazing for this meeting. I have never imagined, and I have never imagined I would come this far. Actually, when I left the meeting 4 years ago, the phone meeting, actually I thought I would never come this meeting. But Stacy told me, come back to meeting. And then, but in my mind, I might not. But so at that time, okay, I don't have enough time, so I'll just. Okay, so I'm going to collect briefly the results, and then these are the people who collaborated or helped me. For white binaries, Karim El-Badri, who is at Harvard right now, and he says he will start professor at Caltech this September. Okay, so there will be also Thursday morning session for white binaries. Okay, so we'll see what are the results. Okay, so Bekenstein and Milgrom's this paper, this is the title of the paper. This is the missing mass problem, similar to breakdown of Newtonian gravity. And I can't imagine why I worked on this because until several years ago I knew little about MOND. So I'm just surprised, and it's just unbelievable. So let's see. Okay. Two sets of data seems to say that if you just predict a theory and then compare with the data in a straightforward way, then the results say yes. Of course, I didn't do sophisticated statistics like Harry, but just a straightforward way of interpreting data, and then of course, even these straightforward calculations were not easy because there are so many complex issues. So I'll try to summarize these results in this time. Okay, these are the papers, and then all papers on rotation curves were published, and then this one is on archive. Okay, so actually, rotation curves and the binary stars are in a sense they are similar. In a sense, the same thing because they have orbital motion, and in galactic disk, the orbits have very small eccentricity, so it is easy to interpret. Okay. And we have two accelerations. One is the you observe baryonic mass distribution, and then you can have this Newtonian gravity. And then the other one is kinematic gravity. That's the observed gravity. Okay, that's the empirical gravity. In binary stars, we have relative velocity, but not the real velocity. It's the projected velocity, so we have to deal with the projection effect. But also, there can be additional star, this one is not observed. When it is binary, only these two are observed. So, but there could be the hidden one. So in this case, the Newtonian gravity is you have to use total mass. And then here is you can also have kinematic acceleration, but this is not radial acceleration because this is from just relative velocity, and the orbit is highly eccentric, and this is the key point. It has extremely highly eccentric, and what you observe is not this velocity, it's the projected velocity, so you have to deal with the projection. And we'll have also a full session on this Thursday morning. Okay, the galaxies, you can have, you can just measure inclination, and so you don't have to worry about projection effect very much. And radial acceleration data are well defined and can be easily compared with the prediction of gravity theories. Okay, but there are some issues, negative issues for rotation curves. That's the radial velocities are not easy to measure, especially in the central region. It's difficult, but for hydrogen gas data is relatively reliable. And also you have uncertainty of mass-to-volume ratios and the merge, and also hydrogen gas to total gas to hydrogen mass ratio. And one tricky issue is that one has to deal with degenerate prediction of dark matter. I think Stacy dealt with this, but you know, if you talk to lambda CDM people, they always say that you know dark matter halos can reproduce. So this is very difficult issue actually when you deal with general people. Okay, now wide binaries. Okay, the most important thing is that dark matter can play no role. Okay, so if you observe gravitational anomaly, then that means gravity must be, you know, different from Newton. Okay, and so it is very good that Javier suggested, you know, white binaries 10 years ago, and but the problem is that we don't know the inclination because the orbital period is so long, it's more than 1 million years. So you have just one period of observation at one period, and you cannot measure the inclination. So you have to measure you have to deal with projection effect, and also unlike rotating disks, eccentricities are extremely high, and this is extremely important. Okay, so actually, stars spend most of the time like well outside of the eccentric orbit. So so let's use an analogy. If we consider comet Halley spent most of the time well outside the solar system. So eccentricity is important, and also this the hidden components that contribute to the total mass. Okay, so there are such issues, but nonetheless, you know, since dark matter cannot play any role, if you discover gravitational anomaly, then that's it. Nobody can argue about it. If you just understand the issues of uncertainties, then you know there's no way, there's no escape. Okay. So I'll go over rotation curves very quickly because Harry also talked about and Stacy also talked about. So basically, this is the prediction of MOND. In this case, actually, AQUAL specific prediction. So if you have this kind of rotation that okay, then in acceleration space, you have this algebraic MOND part, and then if every galaxy is under an external field, so eventually it approaches quasi Newtonian, okay, with modified G. Okay, and also this modified gravity theory specifically predicts this inner behavior. Okay, so I was very impressed about this prediction by AQUAL and also QUMOND have similar prediction on this inner part. Okay, so these are some various predictions. So I was curious to check whether data have signatures of these predictions. Okay, so I separated rotation curves into the inner and outer parts, just like this. Okay, in this case, the inner rising and the outer quasi-flat are well separated. But there are cases it's not well separated. Anyway, I separated all of spark data by eye, and also you can apply more just numerical way, but the results wouldn't change very much. Okay, so skip this. Okay, let's skip this. So this is the okay. This is for the total RLR for the spark data. Okay, here I'm considering these orthogonal beams. Okay, unlike original analysis by spark people. Okay, so if you consider these orthogonal beams, then these are just data. These black no modeling or whatsoever. They are just data Spark database provides. Okay, and then here the dark matter halos were fitted to the data, and then I'm comparing them with the data. And then if you look at by eyes, they are similar, but in detail, actually, there's some difficulty. But the AQUAL simulation results seem to agree better than this. Okay, now I'm going to compare. Okay, now I'm going to do the AQUAL simulation with the standard inputs for the spark galaxies. And then you have these similar results, and also the inner and outer part. Inner and outer part also seem to agree well. And also, this is the important point. If you try to fit all data with AQUAL or QUMOND, then you fail. The required strength of external field is so high that you fail. But if you select only outer part, then you succeed. Okay, you succeed. So, and also the inner part is like that. And this figure alone actually shows that the data, including inner part, it doesn't work. You need to separate inner and outer part. And what's surprising is that the inner part agrees with the prediction of AQUAL. Okay, that's what impressed me most. Okay, so if you just do the straightforward way, you predict what the theory predicts, and then you compare with the prediction of the theory with the data, then you get the overview. I don't need to consider any other way. Okay, now wide binaries. Okay, so for wide binaries, basically under strong external field of the galaxy, Milky Way, this is what you expect. This is what you expect in the acceleration plane. But in reality, due to eccentricity, it starts to deviate, even in the Newtonian regime. And then you expect this deviation. This deviation is not high, but about, if this is 1, this is 1.4 in acceleration. Okay, so you have to, okay. But if you consider this deprojection, these are the points you expect. Even in case of a circular orbit, from deprojection effect, you expect this kind of point. And then for elliptical orbits, you expect this kind of point. So if you do one Monte Carlo, then you get just one of these points. Okay, so there is no hope to constrain gravity with one system. But if you have thousands or tens of thousands of systems, then you can expect these statistical uncertainties will, average out. Then some signals may come out. Okay, so sample selection. Okay, so you can check the paper. And here, what's important is that I had extensive discussion with Karim El-Badri, although he chose not to be on this paper. So this removes flybys effectively. And okay, and then these are the uncertainties of the data. Let me see. And also here proper motion uncertainties are here set by this. And I'm considering two sets. One is the benchmark sample within 80 parsec. Okay, so within this distance, the data quality are extremely good. This is the quality cut. Most of the data already satisfy the quality cut. So if you consider systems within 80 parsec, then you don't have to do any other things. The data are already extremely good. Now, if you go to higher distances, then uncertainties increase. And then I choose that the higher distance data must satisfy the same quality of this benchmark sample. Okay, and that's the idea. And then this is what the referee asked me to do. So I checked that the wide binaries separated by the R value already, agree with the assumption that there are no flybys. Okay, here blue histogram is the what's observed, and then this gold histogram is what you expect through Monte Carlo simulation with only measurement uncertainties. And these are the measurement uncertainties, distribution of measurement uncertainties. And by the way, for the 80 parsec sample, about just 60%, something like that, have radial velocities. But for 200 parsec sample, maybe 30%, only 30% also have radial velocities. Okay, so that's why I consider, this samples is set by R. Okay. Okay, so key ingredients: mass magnitude relation and the hidden components and eccentricities. And then these are the mass magnitude relation. Here I'm considering the additional mass magnitude relation. That's also what referee suggested. That's the internally determined the flame masses, but they are relatively everywhere up to the limit. And then this one goes to only 0.5. Okay, so it has a limit anyway. Okay, so I'll skip most of them. And then here the this multiplicity fraction is calibrated. Okay, this is the important thing. Otherwise, if you don't calibrate multiplicity fraction, then you can get any result you want. You can get Newtonian or you can get Mondian, whatever. So it doesn't make any sense. Okay, so your analysis must show that you should be able to calibrate multiplicity fraction. Otherwise, your result wouldn't be trusted. Okay, because you can obtain any result by calibrating. Okay. Okay, this is one Monte Carlo deprojection result. And then if you repeat this many times, then you get the statistical the uncertainty or the statistical result. Okay, then I first verified with Mach data that this method works. Okay, and also studied the scatter expected in this algorithm. And then these are the typical results you expect. And then these are the largest scatter. These are just the random scatter you expect. And then let's see what the data look like. Okay, this is one Monte Carlo deprojection. And then if you repeat many times, then you can obtain this. Okay, so you see that it agrees with the AQUAL Newton difference extremely well. And then this is non-trivial result. This is amazing. In my whole science, I have never obtained any result like this. Okay, so for example, my paper when I published when I was in Manchester as a postdoc, it was published in Physical Review Letters, and then it was an independent evidence of dark energy at the time, and then it was about 2.5 sigma, something like that. But the whole world shared the result, and then I think that. But these are, if you consider these together, they are 10 sigma significance. So I did additional analysis because the referee requested. Okay, for example, with the radial velocities. So in this case, I throw out all systems without radial velocities. Okay, but I get consistent results. Okay. Yeah. So and here, this is also referee suggested. Okay, so referee made many good suggestions. Maybe because I did any analysis of wide binaries for the first time. So here, if we calibrate multiplicity fraction at this point, then this point, higher point is automatically satisfied. And it should be because it's the Newtonian region. Now, I separated this region, then you get consistent results. Okay. Then I'll skip this. Okay, so the conclusion is that it's amazing. I get the result that both galactic rotation curves for the past 3 years, and then this binary, they agree with the modified gravity. Yeah. So although it is just non-relativistic Lagrangian theory, it agrees. And in science there is no 100%, but I'm almost 100% sure that these results will be verified again and again. Just like this, Mercury orbit anomaly was verified, and it's a scientific result. And then this will be something like that.
Sorry to laugh. You don't have to pick me next time. I will have a question almost every time. Thank you, Chae, very much for this very exciting result. And I take it, I thought I understand why binaries when we started this work on using it to test gravity independent of whatever matter is doing. I didn't realize there's so much that can draw systematics which can drive the results one way or the other at the time. But trying to understand these, you're very positive on these results, whereas my group here with Ingeniel seems to say give a conflicting result. So I think the subject is still there for discussion. I think this will be a very wonderful opportunity for that to understand what's going on. I understand. So one of the things you mentioned was that the flybys, that's a time-dependent phenomena. So is there room in MOND modeling of, say, Y binaries that allows certain non-instantaneous effect? So for example, MOND, as it presently states, says, okay, look at where object is. I tell you gravity right away. It doesn't matter whatever they had a flyby or not or whatever. It doesn't matter. Okay? But I wonder if that is true as well. Also, how external field, which were important in the past but no longer, whether this time delay, the work of Desmond, for example, could maybe put in more parameters, tell us whether other things also matter in the game.
I'm not sure I understood your point. So you are worried that this, each binary we are observing one time, right? One phase time, and then you are worrying that we are averaging many of these.
Yeah, the normal assumption is it made on some elliptical orbit. That object has always been on some sort of that's it. But with flybys, etc., the orbit isn't really elliptical. We're actually making a very strong assumption.
Oh, okay. So if you want to test modified gravity theory, then that orbit could not be elliptical, right? But here, my main analysis is that I'm doing the Newtonian, I'm calculating Newtonian prediction. And then I'm testing whether Newtonian prediction agrees with the data. Okay, so for Newtonian prediction, it's okay to assume elliptical orbits. Yeah. And then what's interesting, okay, I didn't have time, so I went over very quickly. Very here. So this is what Newton expects, and then if you want to test Newton, then you can assume all orbits are elliptical, And then you can see where the data agrees on this point. And then, as I showed you, the five bin results, these 2 points agree well. If you calibrate multiplicity, whether this point or this point, the other point is automatically satisfied. This is very non-trivial result. Okay? Now, these points go upward. The points go upward. And and that shows gravitational anomaly. And now, whether this gravitational anomaly agrees with the prediction of AQUAL, you are true. We need more realistic calculations, but I haven't done it yet. So this prediction is for just circular orbits. So here we are assuming that circular orbits will have similar circular orbits and elliptical orbits will have similar this boost factor. So the orbits will be very different, but the boost factor may be similar. Okay, so that's the limit of this analysis. So for more rigorous check, that's okay. So that doesn't change. So your question doesn't change this anomaly because that's a test of Newtonian theory. So as far as Newton's theory goes, what I did is just as complete as can be.
Yeah. I don't want to take up all the discussion. Please, I ask people to ask questions.
Yeah, so there'll be a session of white binaries later on Thursday, as you were saying. So I don't want to talk about that in too much detail. One thing I just wanted to say, if you go to the slide where you show the G against Gn, so a bit later on. So yeah, this one or the one later on where you have 5 points maybe?
What?
Maybe the slide after where you had 5 points.
5 bins?
Yes, so things like, yes, this kind of thing. So just one general comment I have is that, yes, so in MOND the prediction would look very much like the sort of pink line you've got there because of the galactic EFE. But one has to bear in mind that the low acceleration data come from systems with sort of larger separations and perhaps lower masses to some extent. So the impact of various uncertainties in the problem, including measurement uncertainties with other effects, can be larger at lower accelerations. And because you're talking about velocities, typically the relative velocity you measure will be sort of higher than the actual relative velocity due to the impact of uncertainties. So in general, the impact of unaccounted for systematics would be something like the MOND signal, which is why some of the comments I've got regarding this sort of graph is that one really needs to demonstrate like a flattening at the low acceleration end in order to prove that you've entered what is called the quasi-Newtonian regime, where it's basically G goes to 1.4 G, as you say. So that's just a general comment I have about this.
There's a comment here.
Well, I was extremely happy to see these results of yours, because obviously they agree with what I've been saying for the past few years. And they are nicely complementary to what I'll be showing on Thursday, because you have a very large sample with which is sort of a orthogonal cut to the way I've been doing, which is to try and, rather than model the hidden fraction, the hidden multiplicity factor, to try and get rid of it as much as possible and to have an extremely clean sample that that reduces all these effects, no? That absolutely gets rid of as much as possible of any hidden tertiaries and so on. Of course, my sample is much smaller, just a few hundred systems, but as you say, if you find a small system, a small sample, where you can definitely rule out a Newtonian expectation, then later we can worry about exactly what this means. So is it MOND, is it AQUAL, is it modified inertia? Who knows? For example, as Indranil was saying, in that lower left-hand plot of yours, you see it's not clear that the thing is actually flattening. No? So the AQUAL versus Newton prediction is for a flattening, whereas the deep MOND prediction is for that thing to continue rising. No? So who knows exactly what's going to happen in the lowest acceleration regimes. What is clear, I mean, it's not clear if it was seeing AQUAL or deep MOND or what. What is clear is that we're not seeing Newton. I think we can agree with that, no?
Yeah. So
I think that's the crucial point.
So Newton must break down here. Yeah, that's the.
Maybe the last question.
This is perhaps a foolish and naive question, but how do you know two stars are white binaries? They're so far apart, you know, and periods are so long. How do you find these in the first place?
They have to be at the same distance. Yeah, they have to be at the same distance, and also their separation has to be here. The widest separation I'm considering is 30 kilo astronomical unit. That's about less than 10% of the typical stellar separation. Yeah, typical stellar separation. And so you can you can check by chance alignment. Okay, so two stars are close together can be a chance alignment, right? And then if two stars have the same at the same distance, and also the separation is small, then the chance alignment becomes the chance alignment probability becomes lower and lower. Just like a cross section, suppose you have these points scattered, and then you take any space, just a random position in space, and then the chance alignment probability is very low. That's what Karim El-Badri did. And then, so it's not 100%, but this is a statistical analysis, so you can be actually very sure. And also, this subsample with the radial velocities, that's what people asked me to check here. Yeah, here radial velocities. Yeah, here the standard deviation of radial velocity is very high, over 30. So if two stars have the same radial velocities within uncertainties, it is impossible for them to be chance aligned. And then they same distance and
Same distance from what?
from Earth. Yeah,
From what?
here, from here.
From us.
Yeah, from us. Yeah. So that's why this parameter. Where is the parameter? Okay. Yeah. Here. I did it. Yeah. Here. This parameter R is from, Karim El-Badri, and I searched the whole world And then I found Karim El-Badri is the smartest guy. White binary. So I almost backed him for his, I backed him for his help. And then he helped me very faithfully. And then even for my revision, he's helping. He provided me with radial velocities, but so he's reluctant to be on co-author of this paper because this result is so, you know. But he's helping me, and then he said that he would be interested in to see how this result will revive in the next few years. So, you know, that's what I usually do. You know, I can't do everything. So, for example, for rotation curves, you know, this Stacy and Federico are the smartest guys. So I asked them, and then in this case, I succeeded making them my collaborators. So we wrote paper together. So I usually choose one who knows the data better, and then I ask them. And then of course, I could do, I myself could select binaries, but I can't do better than that. You know, they are the experts. So, and the paper describes extensively and demonstrates why their binary sample is really binary. Okay, so I just take them and then use them, and then it's well received, and also the mass magnitude relation and those things I asked him and also some other people I couldn't trust, and then they suggest, of course, I don't take them just you know, blindly. Yeah, I mean, if you are a theorist or observer, then you have to talk to other people. You can't do everything, right? Yeah. So.
Thank you very much.